So this video will go over section 7.9 and 7.10. So let's start with 7.9 and the solid state. So solids can be either crystalline or amorphous. And so this page is about crystalline solids. A crystalline solid has a regular arrangement of particles, and those particles can be atoms, molecules, or ions. And what matters is that they are packed together and in a regular arrangement with a repeating structure. So that's what solids are. But there are 4 different types of crystalline solids. There are the ionics, the molecular, the network, and the metallic. So the ionic solids are coming from all those ionic compounds that form crystals, salts. And NaCl is a typical example, for example. So any kind of solid made of ions will be a crystalline ionic solid. When you have molecules like water, carbon dioxide, any kind of covalent compound that makes a molecule, if they are in the solid state, we will call them molecular solids because they're made from molecules. The particles are molecules. And let's move to the right here where we have the metallic solids. Metallic solids are formed when you have a metal, and typically it's going to be just a single type of atom that is packed together in a regular arrangement, and that's what happens with all kinds of solids, metal solids. So these will be classified as metallic. So typically it would just be the formula or the symbol for that one metal. And then the last type is the network crystalline solid. The network, for example, sand, which is SiO2, the formula is SiO2, forms a network. So you have bonds and it's making a network with a regular arrangement, but it's more loose than molecular or ionic solid. Diamond is also network solid. So these may be more difficult to identify from the formula. So remember, diamond and sand are typical network solids. So an amorphous solid is really different from a crystalline solid. It's because it has no regular arrangement of the closely packed particles. So typically they will form from the same type of materials that would make crystals, but if you don't allow the liquid to cool slowly, it will not give it time to arrange the particles in an orderly fashion, and then you will have an amorphous solid. It's when liquids cool too quickly for regular crystal formation. And very large covalent molecules tend to form amorphous solids because they become folded and intertwined, and they have a hard time, arranging themselves in a regular pattern before it's already too late and they are solidified. So think about polymers, right? Very large covalent molecules that form amorphous solids. You want to think polymer there. Any kind of polymer that is made of very long chains of molecules will not make a crystalline solid. So the examples are glass. So glass typically would make something crystalline if you give it time when it cools down. But if you cool the liquid very quickly, instead of a crystal, you obtain a glass. So glass is a typical amorphous solid. Plastic and rubber are both the kind of amorphous solid that you obtained from polymers. So these are all kinds of different polymers with, you know, different starting polymers that will give these kind of plastic and rubbers. So let's go over section 7.10 on specific heat now. So heat is also a synonymous of thermal energy. And so thermal energy flows from a hot object to a cooler object. So here you have two pictures that are illustrating that. Let's say you're holding a glass of a cup of ice. So your hand is warmer than the cup of ice. And so the heat always goes from the hot object to the cool object. And so here the heat will go from your hand and warm up the glass and warm up the ice and eventually melt the ice. If on the contrary, you're holding a cup of hot coffee, the coffee is warmer than your hand. And so the heat will flow in the opposite direction. It will go from the hot coffee, warm up the cup, and the cup will warm your hand. So every substance, we can see that it's an example that every substance can absorb or release heat. And a physical property of each substance is how much its temperature changes as it absorbs heat. And the property we use for that is called specific heat. Specific heat tells you the amount of energy needed to change the temperature of 1 gram of a substance by 1 degree Celsius. So specific heat is the property that allows you to know, how much energy you need to warm up a substance or cool it down. So the specific heat definition is given again here. And now if we change this definition into a formula, it looks like this: specific heat. And so the symbol here will be SH, capital S, capital H. So if we follow the definition, it's amount of energy. So it's heat here, symbolized by heat, needed to change the temperature of 1 gram of the substance by 1 degree. So it's divided by the mass of the substance and by the temperature change that the substance experiences with that amount of heat. So specific heat has a complex unit that is in calories per gram and per degree Celsius, or if heat is given in joules, capital J is the symbol for joule. It's a unit of heat. And so specific heat can also be given in joules per gram and per degree Celsius. Now, if we can modify this formula and have it in this form. If you multiply both sides of the equality of specific heat equals heat over grams times delta T, if you multiply both sides of the equal sign by the mass times delta T, on the side where you have heat over grams times delta T, the grams times delta T will cancel if you multiply by grams by delta T. So you will have heat by itself. And on the left side of the equal sign, you will have mass times delta T times specific heat. And so there you go, you get this formula that says heat is equal to mass times temperature change times specific heat. And so if we only write the symbols, it's heat equals m times delta T times SH. So this formula can be used both ways, depending on if you are looking for the specific heat of a substance, or if you want to know the heat that has been absorbed or released when a given amount of substance goes through a specific temperature change. And so an example of a specific heat, and that's the one for water here. So by definition, the calorie is actually the amount of energy needed to change the temperature of 1 gram of water and change its temperature by 1 degree Celsius. So that's why the specific heat of water, due to the definition of calorie, is 1 calorie per gram and per degree Celsius. The metric system established the unit of calorie, and so this is why it's exactly 1 for water. However, in units of joule, the specific of water becomes 4.184 joules per gram and per degree Celsius. So depending on the problem you are doing, you may need one or the other value of the specific heat. So there are tables of specific heat for common substances. And if you look at them, you will see that metals, for example, typically have a lower specific heat than water, which means you need less energy to warm 1 gram of metal and change its temperature by 1 degree. And that tells how metals are very conductive, because you need little energy to warm them up. Water it requires quite a lot of energy to be warmed up, actually. So let's go through a learning check to see how we use this formula of specific heat. So what is the specific heat if 24.8 grams of a metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? So we have this piece of metal. We know its mass, 24.8 grams. We know the amount of heat that has been applied to it, and it's 275 joules that the metal absorbed. And by absorbing this energy, its temperature went from 20.2 degrees to 24.5 degrees. So here we will need to calculate the temperature change, which means you take the higher temperature minus the lower temperature. And because it's a subtraction here, we keep the least number of decimal places. So it's 4.3 degrees Celsius. So that's the temperature change that the metal went through when it absorbed 275 joules. So the question is asking, what is the specific heat of that metal? So the specific heat, you will need to use the formula that says, yeah, I want to say that in your reference packet, that's the form of the formula you have. It says Q equals heat equals M times delta T times SH for specific heat. But here we have the heat, we have the mass, and we have the delta T, and we are looking for SH, the specific heat. So you will use the formula by dividing both sides by M delta T and get that form of the formula. Heat over M delta T equals the specific heat. So if we plug in the values, the value for heat is 275 joules over the mass is 24.8 grams times the temperature difference is 4.3 degrees Celsius. So you can see here that none of the unit can cancel. They are all unique and they will all stay. And so in the calculator, you do 275 divided by 24.8 and divided again by 4.3. The calculator answer is 2.578, etc. Here we are limited to 2 sig figs by the temperature change. The temperature change has only 2 sig figs, 4 and 3. The energy had only 3 sig figs, the mass 3. So we are limited to 2 sig figs by the temperature change. So 2 sig figs, so we keep the 2.5. What comes after the 5 is a 7, so we need to round up. And so the 5 will become a 6. And so we round this to 2.6. And all units stay, so it's joules per gram and per degree Celsius. So that means this piece of metal will require 2.6 joules per gram and to increase its temperature of 1 degree Celsius. So if you compare this value to the value we had for the specific heat of water, which is in joules, 4.184 joules per gram and per degree Celsius, you can see how this metal here requires less energy than water to be warmed up. And its temperature increased by 1 degree. So let's do another learning check. So how many calories are needed to heat a pot of 1,600 grams of water from 25 degrees Celsius to 100 degrees Celsius? How many calories? So we're given the mass here, the mass of a pot of water. We have 1,600 grams of water. We have a temperature difference going from 25 degrees to 100. So we know we will need the temperature change, which means taking the higher temperature minus the lower temperature. So here it's 100 degree minus 25. The dot in 100 tells you it's significant to the ones, to the degree. So you keep the difference to the degree. So 75 degree is the delta T. And we know it's water, and water has a known value for specific heat. We saw it earlier. The specific heat for water is either 1 calorie per gram and per degree Celsius, or 4.184 joules per degree and per gram of water. So you will use one or the other depending on what is the heat unit that is asked for. And so here what we need is how many calories. So we need the heat in calories. So that tells you you will want to use the specific heat of water that has the unit calorie. So the formula again is heat equals m times delta T times the specific heat. And so this time we will keep the formula as it is because we are looking for heat. And so it's already solved for heat. And so we will only need to plug in the values. And so let's do that. So heat is equal to the mass, 1,600 grams, times the temperature change, 75 degrees Celsius, times the specific heat. And here we will use the 1.00 calories per gram and per degree. So you can see here that this time we have units that can cancel. We see that the grams cancel because we have grams in the numerator and per gram in the specific heat. And the degrees Celsius cancel because we have delta T in degrees Celsius and per degree Celsius in the specific heat. And we are left with calorie, which is the unit of heat, and it's the unit of what we want to find. So in the calculator, you do 1,600 times 75 times 1. And the calculator answer is 120,000 calories. So it's a very large number, so you can use the scientific notation to report that. Both answers are correct. Notice how here we need to keep 2 sig figs because 1,600 grams had 2 sig figs, right? The zeros are not significant. The temperature change had 2 sig figs, 7 and 5. And the specific heat has 3, so it's not limiting. So what is limiting is 2 sig figs. And if you write heat equals 120,000 calories, there is 2 sig figs there. And in scientific notation, and so you can use your calculator, and if you use the calculator, I recommend you do second degree, you see flow SCI engineering, and you change to SCI, enter, and you will see how your number now is displayed in scientific notation. And it's 1.2 times 10 to the 5th calorie. And here it really shows how we have 2 sig figs. So that's the amount of heat needed to heat a pot of 1,600 grams of water from 25 degrees to 100 degrees Celsius.